Many Cisco engineers will sit in front of you and tell you that EIGRP is their favorite routing protocol because it's so stinking fast and it's also robust, it's stable, and it's secure. Guess what? That meets all the tenets of a good design networking protocol. But here's the other thing. It should be more people talking about it because RFC 7868 made EIGRP an open standards protocol. However, not many vendors adopted it because they did leave out one very important feature for EIGRP design. We are going to talk about it. I'm not going to spoil it for you. But by the end of this skill, you'll understand a lot more about how EIGRP functions and how we can design an EIGRP network to be scalable, stable, and secure. Let's get going. So now it's time to actually get started talking about EIGRP, and here's the honest truth about EIGRP up front. It has kind of a steep learning curve when you're first acquainted with EIGRP because you have to learn about something called the feasibility condition. The feasibility condition is what makes EIGRP. It's what makes it scalable as well as stable. This is a very important concept to understand, and this nugget is not about the feasibility condition. It's actually about how adjacencies are formed, and this is leading up to the discussion about what the feasibility condition is really all about. So in this nugget, let's get acquainted with the basics of EIGRP, what makes it so different from other protocols, and how adjacencies can really be formed as we start to progress through our EIGRP journey. Let's get going. So our mission, should we choose to accept it, is to understand EIGRP. And really to understand EIGRP, it really does boil down to understanding the feasibility condition so that way we can design our networks with that in mind. The feasibility condition is all about how to determine what is the best path forward as well as what would be acceptable or suitable backup paths to a destination should I lose the connectivity to that best path forward. Now this is all setting up to get into that discussion in a couple nuggets. The first thing we really need to understand is how EIGRP works from the get-go. In other words, we need to understand what makes EIGRP different and how do neighbor adjacencies really form. The first thing that you should know about EIGRP is that it is a distance vector protocol by definition, but it's not necessarily a distance vector protocol in actual action. It does share a lot of the same commonalities of other link state protocols like OSPF and ISIS. Still, in an exam environment, you may be presented with the option to call it a distance vector protocol, which is technically correct, but in reality, it is more like a hybrid protocol. And if I were given an exam choice of calling it a hybrid protocol, this is actually what I would call it. Just know that EIGRP is sometimes defined in two different ways by two different people, depending on whose text you read. It could either be called a distance vector protocol or a hybrid protocol. So what we need to do in this nugget is talk about what does it mean to actually be a distance vector protocol. Let's first start off by talking about what a link state protocol is. That way you can compare and contrast it to what a distance vector protocol. A link state protocol is just like a roadmap. Every router in the entire link state topology or the link state database, this would be an OSPF database or an ISIS database, knows about every single path in the entire topology or area or level or whatever it's communicating with. That way, they could clearly see the point from point A to point B with the maximal amount of bandwidth or the least amount of choke in the network. So a router that's down here that's trying to get to a router that's up here could find, oh, I could take this path and this path and this path and this path to get here. And then it could also find some maybe slower paths or ways to get there. But this is how the link state protocol like OSPF and ISIS is designed to work. Every router shares every link, or in this case, every road that they're connected to, and then they kind of draw a map to get there. The big telling point about this is that they can clearly see what the path from one point to another is like. And this is where distance vector protocols are different. Distance vector protocols are nothing more than this road sign. We know that we're this far away from this place, and as long as we head in that direction, we'll actually get there. This would tell us the quickest way to get there is just follow this road in that direction for this long. This is the vector-like style of the protocol itself. We know the distance and what direction, that's the vector, but we don't know much about the path itself. We just know that to get to that network, it's that far away in this direction. And that kind of is how EIGRP behaves. R3 will learn about routes from R7 or R2, and then it will advertise those routes to R8. But all it says is, I know about these routes and they're this far away from me. Then R8 will learn about these routes and tell R4 about them. It'll say, I know about these routes and they're this far away from me. This is why distance vector protocols are often also sometimes called routing by rumor. R4 doesn't know much about what R3 knows. It just knows what R8 knows because of what it's been told by R3. And it kind of just goes in this circle the whole way around the network until everybody knows about everybody and how far away each person is from their distant network. Now, as we progress through this skill, we're going to learn more about how it determines what's the best path to this network when we explore the actual metric itself and then dig into the true feasibility condition. But the first thing that you should understand is that it does behave like a distance vector protocol in the sense that it only knows what somebody else has told it, and then it punts that information down the chain, and that's how it makes decisions. Now, EIGRP itself, within the Cisco environment at least, comes in two particular flavors. It comes in what's called classical mode, as well as what's called named mode. The named mode has become the evolution of EIGRP over the years. It actually is a different process under the hood, and it has more features available to it. However, if you're learning about EIGRP and you're watching some older content or reading some older textbooks, you may only see EIGRP Classic Mode. Let's jump on R7 for a moment and take a look at what both of these things actually looks like. The cool thing about Classic Mode and Named Mode is that you can run them both on a router. This is one of the ways that we could actually run two EIGRP instances on the same device. So in order to make EIGRP neighbor adjacencies come to life, we can first start off by creating the classic mode of EIGRP. This is by typing router EIGRP and then the first major talking point about neighbor adjacencies, and that's the autonomous system. An autonomous system in networking terms is a system that we have autonomy over. Isn't that a clever name? In other words, it's a system that we have total control over. If this is our enterprise right here, all of these devices make up our enterprise, this is our autonomous system. Now, we are going to talk about autonomous systems in more detail later in this particular skill, but for now, you need to know that this is our autonomous system. And for neighbor adjacencies between routers to come to life, we have to have the same autonomous system. They have to agree we're in the same little system here. We agree that we're part of the same domain. So that's how we can actually secure ourselves and create neighbor adjacencies. So in this particular instance on router 7, I'll call this router EIGRP 10, and this is what makes it classical mode, by specifying the autonomous system number instead of a name. See, if I back out this 10 for just one moment and give it a question mark, you can see we could specify the autonomous system number or a virtual instance name, and this is how we would actually go about configuring named versus classical mode. So I could say router EIGRP 10, and that's created the EIGRP instance in classical mode with all of the classical features of EIGRP. I can also exit out of this. I'll back out my configuration for no router by saying no router EIGRP 10, and now I'll demonstrate how we could do this in named configuration mode. I'll say router EIGRP ENSLD, giving it the name ENSLD. Just like that, now I've created the EIGRP process for ENSLD. And this already sets up one of the big talking points of how named EIGRP differs. Named EIGRP is supposed to be one process for all of the different types of EIGRP we could run, and that's what address families indicate. You see, with address families, I could set up my IPv4 as well as my IPv6 configuration here. So I'll specify IPv4 and hit question mark one more time, and now I can see I can choose to set up IPv4 within a VRF, unicast, or multicast traffic. So I'll specify unicast, and then I specify my autonomous system. In this case, I'll say 10. So the difference between these two is that in classical mode, it was really only designed for IPv4 unicast. Whereas in named configuration mode, we see that we now have the ability to work with address families, which gives us a whole lot more options that we're going to talk about in a later nugget, especially when we get into things like stubs and summarization. Now when it comes time to bring my network to life, and bring up some neighbor adjacencies, we use the network statement in order to actually bring these adjacencies to life. So now I see my IP addresses, and we can actually start to enable EIGRP on these interfaces by taking the network statement. But it's really important to understand what the network statement does under the hood. We type the network statement like 192.168.0.0, and then we specify a wildcard mask like 0.0.255.255, and your initial hunch is to think that this is going to be matching on subnet bits, but it's not. It's actually just matching on bits. It could match on either the mask or the host itself. And what the network statement is trying to do in an IGP in Cisco's world is it's trying to match what are these bits here that could be anything that match a IP address that I have on my interface. It's not enabling EIGRP on a subnet. It's enabling EIGRP on an interface. And the wildcard mask and the wildcard bits here are all about trying to find which interfaces have an IP address that match this, whether it's in the subnet portion or the host portion of the actual IP address itself. It's all about just turning the EIGRP process on an interface rather than trying to match a whole subnet or a specific IP address itself. It's trying to match anything within this range so that it knows where to turn EIGRP on. The big thing that we're taking away from this is the EIGRP runs on the interface that is matched by the wildcard bits. So by specifying just the 192.168 and then anything wildcard mask, it's going to turn EIGRP on for my 3 interfaces. And just like that, it forms a neighbor adjacency right there between router 7 and router 8. That's what this third octet is specifying right here. But notice the next syslog message that's coming up right here. This adjacency is blocked because we're not on a common subnet. Uh-oh, guess what? This is our next talking point. We need to have a common subnet here. This device thinks it has a /24 subnet. What does router 3 think its subnet is? Well, looking at router 3, it immediately tells me what's wrong here is I've actually assigned the wrong IP address to it. It's communicating on 192.168.27 instead of 37. So let's go into this real quick and fix it with Ethernet 02 and say no IP address. I'll copy it from above and paste it. I'll put the IP address in and paste it, but change this to be 37. And almost immediately we have a neighbor adjacency that comes to life. So how did this neighbor adjacency between router 3 and router 7 actually come to life is another big talking point about EIGRP and how it does reliable transmission of data and information using the Reliable Transport Protocol. EIGRP sends hello packets out the interfaces that the network statement matched on. These hello packets are destined to 224.0.0.10. This is the EIGRP multicast address that says for any router that's on this Ethernet segment that is listening on EIGRP, this is for you. Hello, I am out there. Router 3 also sends a hello packet towards router 7, also destined to 224.0.0.10. And then some interesting stuff happens. Once they've seen each other, because they're going to say, these are the hello packets that I've received from other routers, they'll be able to see, oh, you've already seen me. It's time for us to start forming an adjacency and exchanging information. Now, OSPF has a complicated machine that it goes through when it exchanges information. There's elections that happen, not so much in EIGRP. In EIGRP, it begins sending unicast update packets. And these update packets contain a sequence number. The sequence number is at the core of the Reliable Transport Protocol. When it comes time for R3 to send its own update packet, it will specify a sequence number as well as an acknowledgement number that identifies what was the last sequence number that it saw. And once there are no more sequences to send back to each other, it will actually send what is called a hello ACK. It is just an empty packet that contains an acknowledgement saying, I acknowledge the last sequence or update that you've sent me. So this is the gist of it. This is the gist of how information is transmitted between hello and update packets. There's one more packet that we should talk about that's called the query packet. The query packet happens whenever a link or a route goes down, whenever there is a loss of a route. The router that loses the connection will send queries out its other interfaces to its neighbors saying, hey, Do you have a path to this route? And all of the others must reply to this. Now, this is a big talking point that we're going to talk about later in the skill. This is just to set up the different types of packets that exist within EIGRP at this point. We understand now the difference between the distance vector and the link state protocol. We now know that EIGRP has a simpler exchange methodology of exchanging data with the update packets, and we also know that it uses reliable transport protocol, which is really sequences and acknowledgements letting us know what packets it's received. Then there is the query mechanism, which sends out queries to its neighbors whenever a route gets lost. The last thing I want to do here is actually demonstrate it in action by performing a Wireshark packet capture and bringing a neighbor adjacency to life. Let's bring up router 2 and capture what happens on Ethernet 03 right here on the screen. So with the Wireshark packet capture that's running now, we see some hello packets that are actually coming in from 224.0.0.10. That's router 7 that's going across the way up here on this Ethernet 01 link. So let's bring our adjacency to life by going into classic mode, router EIGRP 10, and I'll just turn it on for every interface by specifying all zeros. The adjacency comes right to life very quickly, and my packet capture is full of interesting information. I'll stop the packet capture now, and I'll filter this out by EIGRP. So what do we notice here? Right off the bat, first thing is the timestamp. EIGRP sends hello packets every 5 seconds, and that's exactly indicated by these timestamps that are incremented roughly every 5 seconds. If an EIGRP neighbor doesn't send us a hello packet every 15 seconds, we consider that neighbor dead. This is called the dead interval, or sometimes it's called the hold timer. Now, worth pointing out that on slow links, like WAN links or serial links, this is multiplied by a huge number, 60 and 80. The key thing to keep in mind is that the hello packet is one number, and then the dead interval, by default, is multiplied by 3. Now let's scroll down to the fun stuff whenever some hello packets started happening here. Notice here, we sent and received 2 hello packets with the multicast destination. Once we saw each other, we moved immediately into the updates, which were unicast packets. If I dig into one of these unicast update packets, we can scroll down and we can see, look at this. The payload itself contains the known routes that we know about because we've learned about them either by rumor or because we're directly connected to them. Now, some fascinating info about these routes is where the metric actually gets calculated, and that's what the next nugget is going to be all about. How does it determine what's the best path forward, and what metrics does EIGRP use? That's what we're going to talk about in the next nugget. This has just been setting up how an EIGRP neighbor adjacency is actually formed. I hope this has been informative for you, and I'd like to thank you for viewing. Now, at the setup of the previous video, what we talked about was the feasibility condition, or at least we introduced that there's this concept of the feasibility condition. Then we walked through the steps of how to get a neighbor adjacency brought to life. They then started exchanging information back and forth to each other, and that's what this nugget is actually all about. What is the metric that is actually used in EIGRP to determine the best path towards a destination? This is going to be the core component that is used in the feasibility condition that we're going to talk about in the next nugget. So in this nugget, let's get acquainted with the actual metric of EIGRP and how a calculation to the best path actually occurs. Let's get going. In the previous nugget, we hinted at where we were going, and that's going to be now to the EIGRP metric. How does it actually calculate how far away a specific network is? How do we determine what our best path to a network is? It all comes down to the EIGRP metric. Now, I've got the Wireshark packet capture up here, but I'm going to kind of shrink it down and hide it for right now because it's going to spoil all the fun for us. I'm going to put it right behind my head, and we're going to come back to it in just a moment. First, we have to understand theoretically how does the EIGRP metric really work. The EIGRP metric is comprised of 5 components or 5 metrics or things that it uses in order to calculate its big number that it determines how far away a network really is. Those are bandwidth, delay, reliability, load, and MTU. These are often referred to as the K values because the actual formula for calculating the EIGRP metric is very complicated. There's a lot of math to it, and these are all represented by Ks. This could be K0 through 4. At the end of the day, here's the real kicker. reliability, load, and MTU are subject to change, or at least the MTU isn't as subject to change, but reliability and load are subject to change, and the MTU is often more or less not used. So in the actual K-value calculation where it comes up with the metric, these are multiplied by 0. In other words, they're not used at all in calculating the metric. Bandwidth, however, is used, and delay is used in calculating the metric. So let's pretend for a moment R4 is going to try and find its way to this segment right here between R3 and R7. R4 needs to know some information about the links that it's being advertised from R2 and R8. It needs to know what is the lowest bandwidth that's used in the path and what is the sum of all of the delay. So I'm going to write sum right here next to delay. Let's pick apart these two, bandwidth and delay, one at a time. Think about this theoretically for a moment. If this link is gig, and this link is gig, and this link is fast Ethernet, 100 megs per second, what is the absolute fastest that this R4 could transmit this way? The fastest that it could possibly transmit it is the fast Ethernet speed of 100 megabits per second. It's kind of like you're only as strong as your weakest link. That's why in the calculation, these routers have to tell each other what is the lowest bandwidth that I've seen on my way to get to this particular link. So the flip side of it is if this is gig, and this is gig, and this is gig, R4 could immediately determine that this path may be a faster link because it has a higher bandwidth from one end to the other. The flip side of that is delay. If it takes R3 1 second to process a packet and forward it to this link, and then R2 takes 1 second to process a packet and send it to this link, and then over here it takes 1 second to process this link, you could see how in order to process a packet, it would take 1 second to get to here, then 1 second to get to here, and then 1 second to get to here, and the end result is we have 3 seconds is our total delay to get from one end to each other. So EIGRP, when it's calculating its complicated metric through all of that crazy math, it's going to keep two things in mind in determining what is the best path to get to its destination. It is what is going to be the lowest bandwidth that I've seen on my way to this destination, as well as what is the sum of delay that I've seen on my way to this destination. So with those two things in mind, now it's time to think about the actual behavior of EIGRP itself. There's going to come a moment where R3 or R7 want to advertise this link. Let's pick on R7 now, since we've been picking on R3. R7 knows its metric in order to get into this segment. It's looking at the bandwidth on its interface, as well as the delay on its interface, and it performs the calculation to come up with a metric. Let's theoretically make up something right now, like it's made up the metric 150 is what it calculated between the lowest bandwidth and the delay. Now it comes time for R7 to advertise it towards its neighbors, R8 and R2. How then does R2 and R8 perform their metric calculation? Well, R7 is going to bundle its packet up, and it's going to tell it what its lowest bandwidth is that it's seen so far, as well as the delay. But it's not considering the egress interface when it does this. That's what it's not doing. It's saying, from its point of view, to exit out to this link, that's what it's calculated. So when R8 receives this information, R8 now has to say, in order to get to that link, I need to consider if I have a lower bandwidth and add my own delay on this exiting interface towards the destination to the calculation. So now let's actually see that in action, because that's kind of a complicated thing to grasp and wrap your head around. What we're looking at again is R2's perspective. We're looking at the E03 interface. This subnet right here is the 192.168.37.0 subnet. So R7 has advertised this subnet down towards R2. If I look in the actual payload of the EIGRP packet, this is where R7 was sending all of the known routes down towards R2, and right here I see 192.168.37. So if I expand this out and I drill down into it a little bit, you can see immediately right here. We see things like the reliability, the load, the MTU, the delay, and the bandwidth. All of these things come together to actually form the metric that R7 has discovered about that particular link. So if I look on R7 for its point of view, and I give it a show IP EIGRP topology, we see at the very top of the list, here is this 192.168.37, and a very important and large number, and a very important abbreviation right here. Its feasible distance is this gigantic number right there. I think this is going to be something if I add commas in here. It's 131,072,000. That's the idea here. It's a big number, right? And that's what it used the bandwidth and the delay to come up with. Again, it's a really complicated formula. The feasible distance in this case is what we're going to say is the lowest cost, or the metric itself that we're going to use to get to this particular subnet. And when we arrive at a feasible distance that we can get to this particular network, we install that in the routing table, and the next hop, or the advertising router, becomes what is called the successor. Now look ahead just a moment down here. We see two prefixes, or two installations for the 192.168.38 route. This is the link between R3 and R8. Both R3 and R8 have advertised this prefix to us. And since both of these devices have the default metrics and have the same bandwidth and the same delay to get to this, they advertise the same distance to get to us. When we look in the EIGRP topology table, this is what we call the advertised distance. So what we're saying here is that R3 has advertised its distance of this number to get to this network to us. And R8 has advertised the exact same number, or its metric, to get to the 38 prefix to us as well. Since they are both the same advertised distance, R3's advertised distance, or reported distance is what it's sometimes also called, equals R8's advertised distance, or reported distance, we can safely perform equal cost multipathing, a major design consideration in EIGRP. It automatically will perform equal cost multipathing, or equal cost load sharing, we should say, across both of these routers, since the distance to get to this link is the exact same on from both routers' perspective. Now you may be wondering, well, wait, okay, we understand the advertised distance here, but what is this whole shenanigans about, this 19666? This becomes our feasible distance. So let's look at this in a new way. Looking at it like this, router 8 is now making an advertisement towards router 7. Router 3 is also making an advertisement towards router 7. They're both advertising this link right here that they're directly connected to. So they say our link, our distance away, is this number right here, this huge 131 number. I'm just going to put 131 here just for abbreviation's sake right here. So they advertise this is their connection, their metric right here on this link. But router 7 now has to figure out, okay, well, if it's time for me, router 7, to get to this link, I have to now calculate how much it's going to cost me to get to here, as well as to get to here and add it to it. The cool thing about it is that because the bandwidth hasn't really been changed on any of these, we're not really factoring this in. The lowest bandwidth remains the same across the board. In this actual topology, the bandwidth across the entire topology is 10 megabits per second. So R8 is going to advertise a 10 megabits per second bandwidth this way and say, this is how I calculated it. And then R7 is going to say, well, it's a 10 megabit per second link for me to get to you, so that's really a non-factor for me anymore. Now all it comes down to is, okay, well, what is my delay to get towards you? And as we saw, it was a gigantic number in that packet capture, like 10 million picoseconds or something like that. So what we're looking at here when we see the feasible distance is we've taken the advertised distance and then added our own calculation of what is it going to take for us to get to the next hop. And in most cases, unless there has been a change in the bandwidth link itself, it's just adding more delay into the initial calculation. The big takeaways that you should understand in this particular case is this is one of the biggest ways that you actually perform traffic engineering in EIGRP. As a route gets advertised towards this link, and the same route gets advertised towards this link, we may say, we really wanted to prefer to use one link over the other, so I'll just increase my delay on one of the links and leave the delay alone on the other. The increased delay will then create a higher metric and therefore the other route will be preferred because it has a lower metric or cost to get there. So in that case, there will be only one feasible distance and only one successor route. Now in the next nugget, we're going to take our skills up a notch and really dig deeper into this and talk about the feasibility condition, which is what happens when we have a backup route. We need to understand if it's okay to use that backup route or if it creates a loop. That's what the feasibility condition is all about. In the meantime, this has been understanding how EIGRP metrics are calculated and used. I hope this has been informative for you, and I'd like to thank you for viewing. So in the previous nugget, we understood how EIGRP comes to the decision of what is the best path towards a destination when it calculates that very complicated metric that ultimately is based on the lowest bandwidth on a link and the sum of delays on the links through the path. Now we need to talk about a situation where there are multiple advertisements towards the same route. How do we determine which one of those is best? And can we install alternate routes into our topology table as a backup route? And then lastly, how do we ensure that this is a loop-free path in order to get towards the next route? This is the feasibility condition, and this is the biggest talking point of EIGRP. Let's get going, getting to know the feasibility condition. In the previous nugget, we talked a lot about feasible distances as well as successors and how EIGRP determines the best path towards a destination. And we talked a lot about the scenario where both R8 and R3 are advertising this link right here towards R7. Now here's the kicker. R7 will receive this prefix from R8, right? What's to stop it from turning around and advertising it towards R3? And then let's say R3 installs that prefix into its routing table. What happens then? R3 would route it up to R7, who would then turn around and route it back to R3, who would then turn around and route it back to R7, who would then turn around and route it back to R3, and all of a sudden we got ourselves a routing loop because R8 advertised a prefix which then got forwarded down to R3 when it shouldn't have been. This is where the feasibility condition comes into play, and this is how EIGRP creates a loop-free topology. A big part about EIGRP design is understanding this so that way we can create a loop-free topology, which makes our network scalable and secure and stable. Picking on the 38 subnet one more time, let's recall what this number in the parentheses meant. On the right-hand side of the slash, this is our reported or advertised distance. I'm going to put AD for short for advertised distance, but a lot of people like to call it reported distance so that it doesn't get confused with administrative distance, which is another topic, when it comes to EIGRP routing. It's a big deal too when we're comparing EIGRP to other protocols. So this is our advertised distance that's advertised to us from R3 as well as R8, and they happen to be the same in this. What our router then did is it calculated its distance in order to get to those advertising routers. Again, by using the combination of the lowest bandwidth as well as adding its own delay into the interface, and it came up with this number right here. This became our feasible distance. Where the feasibility condition comes into play is when we have a second advertisement coming in from somebody else. So let's pretend for a moment that we received the route from R3 first, and that became our feasible distance and our only successor. We then received an advertisement from R8, and it's advertising this particular distance right here. Let's again abbreviate that to 131 for simplicity's sake. What R7 then does at this point is it has to figure out if the second advertising router, router 8, is closer to the destination than router 7 is. If router 7 is actually closer to the destination than router 8 is, it would know, wait a minute, I shouldn't accept your advertisement because this would create a loop. I would send it to you, and then I would send you my advertised distance, which is better, and then you would send the traffic back to me, and then I would send it back to you, and so on. So the way this is done is router 7 compares its feasible distance to the advertised distance. If the neighbor is advertising a distance that is further away than our own distance, we know that we are now closer to the target than they are. And there is no scenario where we should send traffic to them, because they're just going to turn around and send traffic back to us because they're going to say, wait a minute, you're closer than I am, so I should send traffic to you. That would be a quicker path there. So the first feasibility condition that you should know about is when multiple routes are advertised to us, we're going to choose the one that has the lowest feasible distance as our successor route. But then for us to use any other backup routes, they would still have to sit closer to the target than we are. So in this case, R3 is advertising a distance of 131, right? I'm going to write an advertised distance of 131 again for abbreviation's sake. And then we calculate our feasible distance of 196. If R8 were to turn around and advertise a distance of 140 to us, and all other things are held the same, R3 would still be the preferred route, but we would know that they are sitting closer to the target than we are, so this becomes a valid backup route. And the term for this backup route is called a feasible successor. So I know this is where it gets complicated, is all the different terminologies. The first one is we have a feasible distance, which is our calculated path to get towards a subnet. And we have a successor route. When there's one successor, that means there's one best path to get there. When there are two successors, unless we've changed something, there are two equal cause paths to get towards a destination. However, if we see a scenario where there is one successor, but two prefixes, two advertisements installed in our topology table, we then have a feasible successor or a feasible backup route. And the thing to look for, of course, is going to be if the advertised distance from that prefix is less than our feasible distance, meaning they are closer to the target than we are. So looking at R7 real quick, my Ethernet 00 interface is where R8 is advertising a prefix to me. Watch this. If I go into configuration mode, interface Ethernet 00, and I alter my delay to be something like 500, now I'll do show IP EIGRP topology. Look at what we have here. This is the interesting scenario that I'm talking about. Just like I mentioned before, how we could engineer this so that traffic would only go through R3, this is exactly what we've done here. You can see we've calculated a feasible distance, but now we only have one successor route. That one successor route is right here because we see the feasible distance matches. Because I altered the delay that would take me to get to R8, we now see how that has increased the feasible distance to get to R8. But because its advertised distance is still less than the winning feasible distance, we know that R8 is still sitting closer to the target and therefore is a viable backup route or a feasible successor. So this is understanding the feasibility condition and how it comes into play. I hope this has been informative for you, and I'd like to thank you for viewing. Now, EIGRP operates with autonomous systems, and at first glance, this looks and feels a lot like ISIS levels or OSPF areas. Here's the spoiler, they're not. An EIGRP autonomous system is like a completely separate routing protocol. If you run two separate autonomous systems on one router, you have to redistribute between them. So it's very important when you go into designing your network that you keep in mind what the autonomous system boundaries really mean when we go from one autonomous system to the next, and how that might actually manipulate the actual routing protocol and its routing forwarding decisions. Let's get talking about autonomous systems and then sneak in a little discussion about address families. Now, I know that last nugget was really huge, talking about adjacencies and the feasibility condition, but that really is the bulk of EIGRP. The rest of the stuff is relatively easy to understand as long as you start to understand the query domain. Basically, what happens in EIGRP when a link goes down or a link starts flapping is the query domain kicks into play. Let's pretend for a moment that the link right here on R3 were to go down. What happens then is EIGRP kicks into overload and starts sending out query messages to all of the different routers that are participating in EIGRP. And because this is routing by rumor, they're going to keep sending queries to each other until a resolution has been reached. So queries are going to go out this way, a query might come back out this way, and the thing with a query is a router must reply to one of the queries. once it receives one. It either has to say, I know how to get there, or I'm going to find out how to get there. So in this case, if R8's only route to that link was through R3, it's going to punt the query to R4. R4, however, may have that route advertised from R2. So it could reply with a path, which would just behave like an update packet, and it would be responded to with an acknowledgement packet. R8 then forwards the path this way, and EIGRP reconverges. Querying is actually a huge, huge deal when it comes to EIGRP's stability and scalability, because what we've seen here is a basic example of what happens on one link in a topology of 5 or 6 routers. What happens, though, when you have a global network with thousands of devices? All of a sudden, one link goes down, and that query just starts spreading out like a tree, and all of a sudden, EIGRP goes into like, uh-oh status. They call it active status. Active means we're actively looking for the response to that query or new route or path there. And again, every query that gets sent out must have an acknowledgement or response sit back. Otherwise, you get what's called stuck in active. Now, there are mechanisms that help you get out of stuck in active. There are timers that follow up. Hey, are you still looking, still querying? Things like that. And those are things that come up in the expert level certification. But what we're really now transitioning to is once we understand how the feasibility condition and backup conditions work, if there is no feasible successor and a route goes down, we then have a scale or stability problem as the query domain starts to spread. Now, you may start thinking about like the OSPF areas or the ISIS levels, where those were the boundaries of where queries or link state updates could be sent. In EIGRP, we have the concept of autonomous systems, and here's the thing. There's not a huge advantage to running multiple autonomous systems in EIGRP outside of finding a way to limit your query domain. But here's the real kicker here, is there are better ways to limit your query domain than by running other autonomous systems. You see, these routers aren't maintaining an entire database here. They're just understanding what their directly connected routers are talking about, and they find a path moving forward to that. It's not a huge amount of CPU overhead to find a route. The bandwidth chunks that come up with it, there's not LSA flooding that we have to deal with or SPF recalculation. It really only comes up when there's a route change and updates are sent and queries are sent out. So if this were to be Autonomous System 10, and down here we were to have Autonomous System 20, and over here we were to have Autonomous System 30, let's just pretend there's a router here for a moment. A query that takes place in one domain would not be spread into another domain. However, these would be seen as completely separate routing protocols, and in order to get AS20 routes into AS10, or vice versa, we would actually have to perform route redistribution, and these would show up as external routes in EIGRP. So a big thing to think about if you were to go this route and run multiple autonomous systems, maybe you have a large enterprise and you actually have different autonomous systems with different networking teams managing them, and you do route redistribution between them, the big thing to keep in mind is what this does to your administrative distance. I'm not talking about advertised distance, not what we talked about in the last nugget. I'm talking about administrative distance and how routers choose the best path forward. The administrative distance of internal EIGRP, meaning EIGRP that's contained within our autonomous system, is 90. But external EIGRP, which shows up as DEX, is 170. That D stands for dual, or the diffusing update algorithm. In other words, that's the algorithm that is used to calculate the metrics that are used to go from one route to the next, as well as the feasibility condition. So you could have scenarios where something like OSPF would actually win over an externally learned EIGRP route, and that is a consideration you need to keep in mind if you're trying to segment your network based on autonomous systems. But for the most part, because there's not LSA flooding and there's not a gigantic database full of LSAs and information that's maintained on each router, it's very common to just see one autonomous system in small to medium and even some large enterprise networks. Now, in the next nuggets, we're going to talk about other ways to handle these query domains, specifically with stubs. You'll really enjoy that information. In the meantime, that's been understanding what the autonomous system does within an EIGRP network. I hope this has been informative for you, and I'd like to thank you for viewing. Now, maybe the number one way that we can limit our query domain and simplify our EIGRP network, as well as maybe one of the top reasons you see this in hub and spoke topologies, is is the stub router. This is where we tell it to stop sending queries in this direction because, hey, I'm the end of the road. I'm a stub. In this nugget, what we're going to be talking about is the EIGRP stub and how it works to limit the query domain and stop this router from being used as a transit router. Here's that other big spoiler that I set up at the very beginning of this skill. This was the actual portion that was omitted from RFC 7868. Really, like I said, the big reason that you choose to go with an EIGRP design was the ability to limit its query scope. And without this particular feature, not many vendors have actually implemented EIGRP. So anyways, with that being spoiled, let's jump into it and talk about how the stub comes into play. So in the last nugget, we understood the concept of the query domain and the autonomous system. Let's pretend now that we have a big autonomous system here, but this section right here, this center section, is what makes up my core network. And over here, I've added in a R9, router 9 here, and this is just a small branch office. It's very important to me that this branch office participates in EIGRP, but at the end of the day, it is just a small branch office, one of those tiny little box routers, right? And we don't want it to be involved in too much query overhead. Let's think about that for a second. For instance, if one of these routes, like this route right here on R8 goes down, we don't want R2 to send a query to my branch office. And we don't want R4 to send a query to my branch office. Why? Because the risk that we run is R9 could tell R2, yeah, I have a route to R8 through R4, and now all of a sudden this main HQ traffic is starting to transit through my branch office, my small branch router, in order to get to R8, and now we start seeing some smoke coming out of my little small branch router because it can't handle that. We want R9 to just be the end of the line. You can know about my routes, and I want to know about your routes, but don't use me as a transit router. If you lose a link, don't query me. That's what the stub does in EIGRP routers. So check this out. What we're going to do is we're going to bring up the terminal of R9 here, and we're going to configure named EIGRP mode. This is a different and newer way to configure EIGRP that's much more flexible because it has more features as well as the ability to run one process for EIGRP for different address families. This is for IPv6, IPv4, multicast, and even within VRFs. I'll go into configuration mode, and now I'm going to create a EIGRP process, but I'm going to create it by name. In this case, I'll call it ENSLD. Now I have to tell it which address family I want to work with. In this case, I'm using the IPv4 unicast address family. So I'll say address family IPv4 unicast, and now it wants to know which autonomous system am I participating in the first place. I'm going to say autonomous system 10. At this point, you can see on the configuration prompt, I'm in the named configuration mode for autonomous system 10 within the address family of IPv4 unicast. Now, I could specify my network statement right now and bring those EIGRP adjacencies up to life, but what I'd rather do is type EIGRP stub. You can see that's really all there is to it. By default, EIGRP stubs are going to be able to advertise their directly connected routes and summary routes if we want to summarize routes that are sitting behind us. EIGRP stubs, this is incredibly important to know, is that it will not advertise a route that it learned from another EIGRP router. So in this case, as R2 advertises routes to R9, it will not forward that route to R4. That's not going to happen. The same thing goes as R4 advertises routes to R9. It will not forward routes to R2. R9 will only be able to advertise its directly connected routes or a summary address that we put in. Now, as you can see right here, based on the little question mark, we can override this behavior. We can enable it to advertise static, redistributed. We can even set it to receive only and not advertise anything. And then there's something called leak maps, which is a little more advanced, but I'm going to talk about that later. For now, I'm going to leave it on the default of EIGRP stub. Now I can advertise my directly connected routes as well as a summary route. I'll type in the network command, and the adjacency will come to life in just a second. Here we go. The adjacency comes to life. If I give it a show IP route, there we go. We see all of these Ds here. We were able to learn routes from our neighbors, but all of these D routes, they were not forwarded to any other neighbors. Therefore, we cannot be a transit router because we're not advertising any other routes. And beyond that, because we told our neighbors that we are a stub, they will not send us any queries. That's a big part of limiting the query domain. Now, I did mention there was something called leaked maps, and there is even a newer feature out there called stub sites that is pretty fascinating. Here's how they work. Pretend for a moment that we have a couple routers behind router 9. Now we get into an interesting issue, because remember, we learn routes from EIGRP, from these routers over here that are behind us, but because we're a stub, we're not allowed to advertise them out any other routes. So these routers need to get out to R4 or R2, but the traffic isn't allowed to return back because we never advertise those routes towards them. So what we can use is we can use something called a leak map. The leak map is basically a route map that identifies these routes and allows them to be leaked out these interfaces, and it allows other routers to query us about those routes. This is a more complicated way of doing things because now we have to create route maps, and then we have to specify the leak map on each of the interfaces that we want to leak traffic out of. And that's why they kind of overhauled EIGRP in recent history and created something called stub sites. Stub sites is a feature that is only available in named EIGRP mode. But basically it handles a lot of that heavy lifting for us. Within a stub site, we tell all of these routers that are in the site, you're in a stub site. And then on our main head router, we say which of our interfaces is a WAN interface. That's pretty much it. Once the router knows where its WAN interfaces are, any routes that it learns on the WAN interface will not be advertised out the other WAN interface. But all of the other routes that it learns, it will advertise it out, and it will allow queries for those specific routes. So that's been understanding how stubs come into play, and it helps you limit your query domain, but still has some flexibility in what we can or cannot advertise out of our links. I hope this has been informative for you, and I'd like to thank you for viewing. Just like all other routing protocols, summarization is going to be a big part of limiting our query scope within EIGRP. In this case, what we're going to be talking about is where we could put in our summarization points in an enterprise network. EIGRP behaves a little bit differently than you may be expected to, because instead of summarizing as it leaves a domain, what we're actually talking about in EIGRP is summarizing on each individual link. This is a pretty unique feature that makes it a distance vector protocol. We're also going to take it up a notch and talk about a little more of an advanced topic like leak maps. Don't worry, you don't really need to know this for the exam, but it is an interesting feature that you should know about when you get into the real world. Let's get going. So it was only a matter of time till we jump back to this diagram, right? This is the 3-tier enterprise design that we're so used to seeing, and now we're talking about it in the context of EIGRP. Now, in the past, if you followed along in this playlist, you may have seen the content on ISIS or OSPF, and you would have seen the concept of levels and areas and how those broke up the actual IGP routing domain. Whereas with EIGRP, we're simply talking about one gigantic autonomous system, aren't we? This whole thing would be one autonomous system, but each router, again, within the autonomous system, only knows what its neighbor knows. It doesn't care about what these devices up here knows. Switch 1 here only cares about what these neighbors here know about. It's routing by rumor. So we don't have this gigantic topology or gigantic database that we're trying to control. Rather, what we're trying to control is the size of our routing tables and the size of our query domain. So what we may do within this autonomous system where we have the distribution and access layer, this is where we may start to configure stubs or stub sites. So this over here could be a stub, and this over here could be a stub. Or we may actually configure the actual access layers themselves. This is probably the more preferred design. These to be the stubs, because if a route goes down up here, we don't want to query this device down here on how to get to it, right? This is where we want to limit that. Beyond that, one of the things that can actually help us with limiting our query scope is summarization. And this, of course, also helps our routing tables themselves. Just like we've done in the past, at the distribution layer, we can perform summarization. But unlike OSPF or ISIS, where it basically summarizes everything going outbound, summarization on EIGRP occurs on each individual link. When you configure EIGRP summarization, you have to configure it on all of the links that are running EIGRP in the direction that you want summarization to occur on. That's a big thing to know about, and that's a big traffic engineering tip that you have for you. For instance, right here on switch 6, let's pick on switch 6 for a second. I may perform summarization right here on E00 destined towards switch 1, but if I don't perform summarization on E01, guess what happens? All of the more specific prefixes get advertised out E01, and I've now engineered all of my return traffic to be coming in this direction, because the more specific prefix will always win, won't it? So it's important to keep in mind with summarization in EIGRP that you summarize at the same points that you would in a typical enterprise network, except that you're going to have to summarize on each of the links themselves unless you specifically want to engineer it so that traffic comes inbound from a specific link. That's going to be using the more specific prefixes. Beyond that, remember that concept of a leak map in stub sites where we could leak prefixes out towards the HQ? We can do the exact same thing with summarization. I can perform summarization on both of these uplinks again, but I can create a leak map that leaks a more specific prefix out with the summary route. So let's say I want to summarize the entire 192.168.1.0/24, and I summarize that as it goes out of these interfaces within that specific section of my enterprise. But then let's say I want to leak 192.168.1.8/30 out this specific interface, so that way that traffic always comes in on that specific interface. That's exactly what a leak map can do for you. Now again, how to actually configure that is getting up into that CCIE level expert stuff, but you should know again that there are ways that you can engineer EIGRP to perform summarization, but still manipulate how traffic comes back in using things like the leak map. So that's been understanding how EIGRP would be laid out in a 3-tier enterprise design with summarization and the query domain kept in mind. I hope this has been informative for you, and I'd like to thank you for viewing. Now, just like the other IGP routing protocols, we can implement authentication to secure our neighbor adjacencies with other EIGRP speaking routers. We can also implement passive interfaces, something that you may see in the OSPF content in this particular playlist. So what we're going to do in this nugget is we're going to talk about how security and authentication take place, as well as passive interfaces take place within an EIGRP network. Let's get going. Of course, like all of the other IGPs, we do have the ability to add security within our IGP, especially EIGRP. We're talking about using a sort of password and passive interface configuration. This works exactly the same in OSPF as it does with ISIS. If we don't want an adjacency to come to life, but we do want to advertise that prefix, we can use things like EIGRP passive interfaces. So if I were to go into configuration mode, on R4, let's take a look at the topology one more time. We're talking about this router right here. Let's say I didn't want a neighbor adjacency to come to life right here on R8, but I did want to advertise that prefix down to these two links. We can use a passive interface. Again, this is perfect for when we want to advertise a prefix, maybe on the edge of our network, but we don't want an adjacency to come to life to another organization or like our service provider. That's where passive interfaces can really help secure us. So on R4, I can go into router EIGRP 10, and I can say passive interface and specify Ethernet 01, and there we go. The adjacency between me and R8 has now gone down, but we are still advertising that link of 192.168.48. If I go to R9 and give it a show IP route, we can see 192.168.48 is definitely still alive and well right there, and we can still get to that link even though the adjacency was lost. Beyond that, we can also talk about authentication. And authentication is configured in a couple different ways, depending if we're using the classic EIGRP mode or the named EIGRP mode. On R9, if I give this a show run and pipe that to section EIGRP, you can see we used named EIGRP in a previous nugget. We called it router EIGRP ENSLD or ENSLD. So I'll go into router EIGRP ENSLD, and this will demonstrate how you can configure authentication. Really, the thing that you should know is that you can configure authentication. Knowing how to configure it is more of an NRC topic, but still, it's important to actually see it so that you can practice it and understand the concepts under the hood. Within named EIGRP configuration mode, I have to go into my address family one more time, unicast, autonomous system 10, and now we have to configure specific interfaces to run authentication. Within the address family, I can specify AF interface and then specify the outbound interface that I want authentication to be run on. From here, I can specify authentication, and then I can specify which mode or keychain that I want to use. Keychains, again, come in really big handy when we want to use rotating passwords. Passwords may expire, and then we accept a new or send a new password after a certain deadline. With authentication mode, you can see my two modes that I can run are MD5 or HMAC SHA-256. Again, this is exactly like OSPF. OSPF can run MD5 or HMAC SHA-256, and we configure authentication on the specific interface. All I have to do now after I specify authentication mode HMAC SHA-256 is type in the actual password that I want it to be. I'll say Cisco1, something like that, and press enter. Now my adjacency comes down with R4 because we're trying to authenticate now. And now that that neighbor adjacency is down, this is going to set up a huge talking point about the difference again between named mode and the classic mode of EIGRP. Within named mode EIGRP, we added new features to it, like the ability to do HMAC SHA-256 authentication. Classic mode EIGRP cannot do that. So check this out. We're going to jump over to R4 and I'll show you real quick. I'm on router 4's command line. If I give it a do show run section EIGRP, you'll see really quick how we have this configured. We set up a passive interface on Ethernet 0.1, and we also have basically EIGRP running on all other interfaces. The interface that we would want to configure named configure HMAC SHA-256 configuration would be Ethernet 0.2. But since we're in classic EIGRP configuration, we have to do this on the interface itself. So I'll go to Ethernet 0.2 and I'll say IP authentication mode EIGRP, then I have to specify my autonomous system number, which was 10, and then look at this. My only option is MD5 because classic EIGRP only runs the process with MD5 authentication. That's simply not going to work. I either have to reconfigure R9 to do MD5 authentication, or I have to configure this device to use named EIGRP configuration. So check this out. This is actually really cool, and I wanted to squeeze this one in there. If I go back to router EIGRP 10, I can now say EIGRP upgrade CLI. That will actually convert this process from EIGRP classic mode into EIGRP named mode. All I have to do now is specify a name for the new process, like ENSLD, and I press enter. It says, are you sure you want to convert this? And we'll just say, yes, we do. Now, if I do show run, section EIGRP, check this out. Now we actually have converted into named EIGRP configuration mode. I'll go router EIGRP, ENSLD, address family IPv4 unicast autonomous system 10. I'll go into my interface where I wanted to configure this, which was Ethernet 0.2, and I'll set authentication mode HMAC, not GMAC, HMAC SHA-256, and the password, the password was Cisco1, wasn't it? And there we go. The neighbor adjacency comes back to life. So that's been a big whopper of a nugget. Of course, EIGRP can do authentication on individual links, just like the IGPs. But another factor that you should keep in mind is if you want to use HMAC SHA-256 instead of MD5, you'll have to use named configuration mode. And if you were running classic EIGRP, you can upgrade it to named configuration mode with the EIGRP upgrade CLI command. So that's been understanding authentication and security with EIGRP. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. EIGRP is one heck of a robust routing protocol. It is blazing fast and it has all of those bells and whistles, but it does behave a little bit differently because it is a distance vector routing protocol. We have to keep in mind where summarization points occur, and specifically that they're on links. We have to keep in mind that we don't break up areas. We have to introduce things like stubs to limit the query domain. This is why EIGRP is a pretty radical shift from link state routing protocols like ISIS and OSPF. But it is fun to actually get in there and play with it and see about all the features that it can do. Now, as you progress towards the advanced level or expert level EIGRP, that's where the world really opens up because EIGRP is an incredibly robust protocol with all sorts of features that are baked into it that you learn about when you jump into the CCIE level. So I do encourage you just to be a little curious, maybe explore a little bit about what the other features are, like EIGRP over the top, or the EIGRP add paths features. Why is this deployed on top of a DMVPN again? Because this is such a great hub and spoke topology routing protocol, and that's where you see these advanced features start to pop up. Anyways, that's been an EIGRP design. I hope this has been informative for you, and I'd like to thank you for viewing.